I'm going to talk about probing physics beyond the standard model with neutrinos. And I hope that after Sanjeev's talk, you are well motivated to do neutrino physics. So let me just give you a very brief description about neutrinos. We know that neutrinos are very special. They are the most elusive particles in the universe. They are weakly interacting, and we have only three flavors of neutrinos, which are electron, muon, and tau. And the flavor eigenstates are not same as the mass eigenstates, and there will be the flavor eigenstates, they are related to the mass eigenstate by some unitary transformation. And this requires that the neutrino oscillation, this requires that the mass eigenstates are like linear combination of flavor eigenstates, and we can observe the neutrino oscillation from various experiments, and which requires that neutrinos, they have to be massive. But the masses of neutrinos, we measure two mass square differences. One is solar mass square difference, which is of the order of 10 to the power minus 5 eV square, and the other one is atmospheric neutrino mass square difference, which is 10 to the power minus 3 eV square. So if we take the square root of the mass square differences, then we get the neutrino masses to be sub-electron volt range, and all the other standard model fermions, they are having masses from say 0.5 MeV to up to 172 GeV of the order of TeV or 0.1 TeV. So we do not know why the neutrino masses are so less in comparison to other fermion masses. So we already learned about how to generate the masses for the neutrinos. Srubabati already discussed. I will just briefly mention about the simplest mechanism to generate masses for the neutrinos. And the standard model gauge group, we know that this one is the standard model gauge group, and these are the standard model particles. In the quark sector, we have both the quark doublet as well as up type and down type right-handed singlets. Whereas in the lepton sector, we have only left-handed doublet and the right-handed singlet for the charge leptons. So to generate the mass, we need the Higgs, and the vacuum expectation value of the Higgs that will give the masses to the quarks and charge leptons through the equa interactions. The equa interaction, basically it couples to a left-handed particle to the right-handed particle. So unless you will not have the right-handed counterpart, you cannot generate the masses, and notice that there is no right-handed particle for neutrinos. Therefore, we cannot have masses for neutrinos in the standard model. So how to generate the neutrino masses? The simplest possibility is that you can simply just add a right-handed neutrino, then you can use the same mechanism which is used for the mass generation for other particles, then everything will be solved. So you can just add the right-handed neutrinos, which will transform under this under the group standard model group in this way. So you can have the corresponding Yukawa interaction. You have a left-handed lepton doublet and you have the right-handed particle. So you have this Yukawa interaction, which will give you the mass for the neutrinos in this way. However, as we think this one is like the simplest mechanism, it's very obvious. However, it's not that obvious, and because the Yukawa interaction term or the value of the Yukawa interaction, to get the sub-eV scale mass of the neutrinos, you need very small Yukawa coupling, which is like 10 to the power minus 10 or 12 orders smaller than other Yukawas. So why we have the such different behavior for neutrinos? This is not understood. So what we have to do, instead of having just simply adding the right-handed neutrinos, we have to do something. And Srubabati already mentioned about the CISO mechanism, which are the standard way to generate the neutrino masses. So the master formula here is the SU2L, or if you take the SU2 group multiplication, then you will have 2 cross 2 is equal to 3 plus 1. So the first possibility is, generally when you combine the left and right-handed particles to have the equivalent interaction, you have to combine L and phi tilde, so that you can have a singlet here, and then you add the right-handed neutrinos to get the equivalent interaction. So this, when you take the combination of L and phi tilde, you will get the multiplication like this. These are the SU2L and U1 combination. So you are getting 1, 0 and 3, 0. So out of these combinations, we have to get a singlet. So when we take possibility 1, this one, then we need a 1, 0 to get a singlet, and when we get this one, we need a 3, 0, because 3 cross 3 is 5 plus 3 plus 1. So to make a singlet, either we have to take a 1, 0 or 3, 0. This is one way we can generate the neutrino masses. The second possibility there is that you can also take L bar and LC combination, and this will behave like this is the group multiplication under SU2L and U1Y. This will give you 1 plus 2 and 3 plus 2. These are plus 2 are hypercharges. So to make singlet, for this one you need a singlet and hypercharge minus 2. For this one you need a triplet and hypercharge minus 2. However, the singlet, it transforms like this way. To understand this one, you can take the simple example of how to combine two spin half particles to get singlet. So for the singlet, you know that spin up, spin down, minus of spin down, spin up. So this cannot combine a neutrino to neutrino. So this possibility is not possible. So whatever is 3 minus 2, this one is allowed. So 3 minus 2 is give you 1 singlet, and minus 2 plus 2, it will give you again U1 singlet. So the possibilities are 1, 0, 3, 0 and 3 minus 2. So when you take the SU2L singlet and hypercharge 0, this one is known as type 1 CISO. When you take SU2 triplet and hypercharge minus 2, this is a scalar, this is type 2, and this is type 3. So pictorially, you can represent these mass generation in this way. First one is type 1 CISO, where you are adding a right-handed singlet neutrino, and second one is scalar triplet. You are adding 3 minus 2. This one will give you the mass formula in this way. This is type 2, and when you add a fermion triplet, it will give you the mass formula like this. So if we want to have a sub-eV scale neutrino mass, then our whatever be the new particles that we are adding, they have to be very heavy to get this one, small value of this one. That is why these mechanisms are known as CISO mechanisms. So all we know that the flavor eigenstates, they are related to the mass eigenstates by this PMNS matrix. So we can parameterize this PMNS matrix by 3 mixing angles and 1 phase. And Sanjay has already given you the assignment why this CP phase is coming in S13 sector or 1,3 sector. So all these mixing angles, they are very precisely determined by various experiments. However, we do not have any idea about the CP violating phase delta CP. Although we have some rough idea from ANOVA and T2K experiments, but that value is not very precise. Now, coming over to this neutrino mass matrix, since the S13 value is non-zero, then you can include the delta CP parameter along with S13. So this allows us to have CP violation in the neutrino sector, because you need large CP violation to explain the baryogenesis or the matter dominance of the universe, and whatever be the value of the CP violation that you get from the quark sector, that is not sufficient to explain the baryogenesis or the matter dominance of the universe. So we need extra sources of CP violation, and since S13 is not equal to 0, and you can have also CP violation in the lepton sector, that gives us a better idea to explain the matter dominance of the universe. Now next, since CP violating phase is non-zero, then you can characterize that CP violating value by Charles-Cogue invariant, and you all know that this Charles-Cogue invariant this gives the measurement of the CP violation, and it doesn't depend on the parameterization. So you can also consider the Wolfenstein parameterization, and you can find out what will be the value of this JCP. So JCP, it depends on all the mixing angles as well as sign of delta CP. So if any of the mixing angle will be 0, then you won't have CP violation, and even if the delta CP value is equal to 0, then you won't get CP violation. So to get maximal value of CP violation, you need the delta CP value to be pi by 2, because it is coming as sign of delta CP. Now, if we put the measured value of the mixing angle from the quark sector, then the CP violating parameter is coming out to be of the order 10 to the power minus 5, whereas if we put the values of these all the mixing angles and say delta CP to be pi by 2, then the leptonic CP violation, it is coming out to be 10 to the power minus 3. So this CP violation, it can be searched in various long baseline experiments, and at present we have a rough idea about the value of the delta CP from currently running long baseline experiments T2K and NOVA. Okay, now we have to discuss about how to prove the new physics beyond standard model with neutrinos. So the main assumptions that we use to prove the physics beyond the standard model is the neutrinos, they have only standard V minus A type of interaction. We do not consider any other type of interaction. So your vortex that or charge current vortex that neutrino will have the interaction with the W boson, it always have the structure as gamma mu 1 minus of gamma phi. Then the next assumption is used is that there are only three flavors of neutrinos. Then also we use the assumption that the PMNS matrix is unitary, that is the matrix which relates the flavor and mass eigenstates, it has to be unitary. We also do not know what is the nature of neutrinos, Dirac or Majorana, and these are the three mechanisms generally used to generate the light neutrino mass: type 1, type 2, type 3. Type 1 is for additional right-handed neutrinos, type 2 is for additional scalar triplet, and type 3 corresponds to additional fermion triplets. So to generate, it is obvious that to generate the neutrino mass, you have to have additional heavy particles or new particles, which is inevitable. And since neutrinos are special, they can provide ideal platform to explore BSM physics. Now these are again all the unknowns I have listed. We do not know the absolute values of neutrinos. We do not know the nature of neutrinos, whether it is Dirac or Majorana. We also do not know if there is any extra flavor of neutrino, which are basically termed as sterile neutrinos. We also do not know whether the PMNS matrix is unitary, then mass ordering and octant of theta 2, 3, etc. Then another point you have to see is here that the mixing matrix in the quark sector, which basically relates the down type quarks flavor eigenstate to the corresponding weak eigenstates, it's almost hierarchical. That is, the diagonal elements are order 1, whereas the off diagonal elements, they are suppressed with respect to this lambda. And for the PMNS matrix, the structure is like this. It is not hierarchical. That is, the neutrino mixing angles, they are quite large comparison to the quark mixing angles. So the origin of neutrino masses and mixing at more fundamental level, this implies the physics beyond the standard model. So by studying the properties or the oscillations of neutrinos, we can understand various type of BSM physics, like what are the non-standard interaction, whether neutrinos can we get any information about the CPT Lorentz violation, etc., etc. Okay, now this is a pictorial diagram. Collider experiments, they give you the new physics when the couplings are very large and mass scales are also large. Whereas our standard model is sitting here, where the couplings are large, but masses are very of the order of say GeV or up to 0.2 GeV. Whereas neutrino experiments, they are very special because they can explore the regions in this parameter space where the couplings are very small as well as the mass scale is very small, because neutrino masses are very small. So the first BSM scenario I am going to discuss is the sterile neutrino. This is a very simple extension of the standard model. So we know that the sterile neutrino or right-handed neutrino is absolutely essential to generate the neutrino mass in the canonical seesaw mechanism. So similarly, you can have many scenarios in which you have extra neutral fermions. So these right-handed neutrinos, they interact with the standard model left-handed lepton in this way to give you the Euclid interaction, and that will give you the masses. But here, although it gives the Euclid interaction to generate the masses, but it doesn't give how many neutrinos are there. So similarly, these right-handed neutrinos, they will give you the, or they can generate the Majorana mass term, but it doesn't tell you anything about the scale of this right-handed Majorana mass. So you can have the masses of the sterile neutrinos from various ranges. So if you have the same mass scale of the order of electron volt, then you can probe such sterile neutrinos in short baseline experiments. Similarly, if you have the masses of the sterile neutrinos of the order of keV range, they can be considered, or they can contribute to the relic density, and they can be considered as sterile neutrino dark matter. Similarly, if you have GeV or TeV scale sterile neutrinos, then you can have leptogenesis, and they can give you the they can provide the explanation for the matter dominance of the universe. Okay. Now, to know about the number of, say, active neutrinos, we can get the information from the invisible decay of Z boson. So we know that if the Z boson, it decays to, say, hadrons through QQ bar, to decay to charged lepton pair L plus L minus and nu and nu bar. So this is the, say, in the parameter space of scattering cross section E plus E minus to versus energy. These are the experimental data, and if you want to fit the, we know very precisely what is the mass of Z boson and what is the width. Then if you want to fit the cross section with the number of neutrinos, because there will be, say, these are invisible width. So if you take n equal to 3, then your experimental data is quite, you can explain the experimental or fit the experimental data quite well. Similarly, from Evans-Stock, we know that from cosmology, we get to know the number of neutrinos of this. This is the value of n nu, or number of neutrinos. So if we take into account these values of number of neutrinos, then there is no space for extra sterile neutrinos, or no space for light scale active neutrinos. But if the neutrinos, they do not couple to the Z boson, then they can be treated as sterile neutrinos, and you cannot get their signature, or you cannot infer their signature from these experimental data. So the first, these things are already discussed by Uma Shankar, but I will just briefly list the things here. So the first hint of light sterile neutrino, it came from LSND experiment, and this experiment, it ran during this period 1993 to 1998 at LNL. So they used basically the pion decay to generate the neutrino beam, and you can see that the pi plus, it decays to nu mu and mu plus, and this mu plus again decays to this one. They stopped their sister particles pi minus, so you can have nu mu bar and nu e. So then they want to see this nu mu bar to nu e bar, because we do not have any nu e bar source in our beam, and there is 3.86 sigma excess here, and if you take L by E value of this one, then it gives the hint for delta, the neutrino oscillation for delta m square equal to 1 eV square. But till that time, we knew only the two mass square differences, solar and atmospheric. So this new mass square difference, we cannot fit in 3 neutrino scenario, oscillation scenario, which implies that there will be one extra sterile neutrino. Similarly, to verify the experimental result of LSND, minimum performed again. Here the technique is different. They considered pion decay in flight, whereas the LSND experiment considered pion decay at rest. So they have also observed 3.4 sigma excess in nu E and 2.8 sigma at nu E bar events. So this is also consistent with the LSND experiment. Similarly, another is reactor anomaly, where in the neutrino flux, it is not consistent with the expected one, and there is around some 3 sigma deficit found in reactor anomaly. However, recently a new analysis, it finds that this discrepancy between the reactor neutrino experiments and theory, this may be a result due to the analysis of the electron data, and after that it is considered that reactor anomaly has gone. So microboon, they want to verify whether there will be sterile neutrinos or not, and in microboon results, it shows that there is no excess in nu E events coming from nu B. So though they published their result, one group, Denton, they studied that they considered, or they have reanalyzed the data of microboon, and they said that it is still possible to have EV-scale sterile neutrino. So in reply to this paper or this comment, microboon again performed a joint fit, taking into nu E appearance as well as nu E disappearance channel, and they have shown that the 3 neutrino fit, it gives a better fit than 4 neutrino fit at 1 sigma. In addition, a combined fit of miniboon and microboon, it shows that 3+1 model is still allowed at a significant confidence level. That means the present situation is like that. We cannot completely rule out the existence of sterile neutrino, neither we can conclusively say that the sterile EV-scale sterile neutrino is there. So these are the summary. So if there will be a sterile neutrino, then your 3×3 mixing matrix will become 4×4 like this. There will be mixing of the active neutrinos with the sterile neutrinos, so you have this one. So to parameterize any n cross n matrix, we know that you need n-1 times n-2 divided by 2 mixing angles, and n-2 minus n-3 divided by 2 phases. So for 4×2 parameterized 4×4 mixing matrix, we need 6 mixing angles. In addition to the standard 3 mixing angles, we need another 3 mixing angles like this, and additional 3 phases. So if we take the limit, because if we consider the consider 3+1 scenario, then one mixing angle or one mass square difference is coming out to be EV square. So if we take similar to the previous case, like 1 EV square is much larger in comparison to 10 to the power minus 3 or 10 to the power minus 5 EV square. So we can take 2 flavor oscillation, then the oscillation probabilities are coming like this. And here sin square 2 theta alpha beta, it is related to these mixing parameters. Similarly, this is appearance probability, this is disappearance probability, and in the 2 flavor scenario, these expressions are coming like this. So Nova and T2K jointly, they searched for this 3+, or they want to verify this 3+1 scenario. So here the black solid and black dotted lines are with for 3 flavor scenario with 68% and 90% confidence level, and the shaded regions are with 3+1 flavor scenario and 4 neutrino scenario. And this one is the sin square 2 theta 3 range, currently allowed range, and these are the best fit values. This one is black one is for 3 neutrino scenario, and red one is the 4 neutrino scenario. So if you consider sin square 2 theta 3, then you can see that there is no discrepancy. However, when you come to this sine square theta 2 3 and delta m square 3 1 plane, you can notice that the best fit values for 3 neutrino scenario is quite different from the best fit values for say 4 neutrino scenario. One is in lower octant, other one is in upper octant. So we need, or the upcoming short baseline neutrino oscillation experiment at Fermilab, they will provide us better information whether our 4 neutrino 3 plus 1 scenario is, or there is any EV scale sterile neutrino is there or not. Similarly, again, these are the NOVA result for the allowed mixing angles in say theta 2 4 and theta 3 4 plane, and this is u mu 4 and u tau 4 plane. So far we do not have, or there is no conclusive result from NOVA and T2K. Now coming over to, so from neutrino oscillation experiments, we do not have any conclusive result about the existence of fourth sterile neutrino. Now let us come to say results from flavor sector. Recently, this is the result from Bell 2 experiment. They were looking for this B plus, this is a B meson decaying to K plus and nu bar. So this is their experimental result, and this result is having 2.7 sigma deviation with the standard model result. However, if you take the values and take the best fit values with the earlier result, then this value is coming out to be this one, and again this one is having more than 2 sigma deviation with respect to the corresponding standard model prediction. So there are many scenarios which can explain this discrepancy, but one of the attractive scenario is that there should be additional decay channels with undetected final states like sterile neutrinos, dark matter or long-lived particles, but this light sterile neutrino are well motivated, and you can consider this one as indirect hint for the existence of light sterile neutrino, but mind that these sterile neutrinos, they should be higher than EV scale sterile neutrino. They could be say MEV or GeV scale sterile neutrinos. Okay, so this one is the first part. Now let us come to the non-unitarity of the neutrino mixing matrix. So basically we consider our neutrino mixing matrix to be unitary, that is U dagger equal to 1. So this implies that if you take the product of the one row or one column of the matrix and multiply with the complex element of other column and take the sum, that will give you 1. That is U dagger equal to 1. So this is the unitarity condition. Now in the quark sector, we also have the CKM matrix, which is again unitary, and we precisely measure the values of the CKM mixing angle as well as the CP violating phase. These are the corresponding values, and if we want to verify the unitarity of the CKM matrix, there are various measurements, like we can have CP violating parameter from K meson system, we can have CP violation from meson system, mass square differences, B0 bar, BS bar. So there are many observables which can be used to fit or to constant this unitarity triangle. However, in neutrino sector, we can have only appearance probability measurement as well as disappearance probability measurement. But the advantage is that we have several experiments. So if we take the values of, say, if you see the values of the lepton mixing parameters, these are given here, they are quite different from the quark mixing parameters. So this is basically the unitarity relation, U dagger equal to 1, as well as this is the, if you take U alpha I, U beta I star equal to 0. So when you expand this one, it will give you like this kind of relation, and you can consider this as, or you can represent this relation as a triangle in complex plane. So this relation you can write or you can present like this. This can be a triangle in a complex plane, and if this triangle is non-zero or non-vanishing, it has some finite area, then it will give you the measurement of CP violation. Then to draw this diagram or to have the unitarity triangle, you can reparameterize this one or renormalize this one and take the vertices, one at the origin, one at 1, 0, and one is rho xy and eta xy. That will give you the tip of the unitarity triangle. And this one is related by this expression. So these parameters are given here. So here you can see that this is a representative value of the lepton mixing matrix unitarity triangle. So if you take the present data, this is the origin 0, 0 vertex, this is 1, 0 vertex, and this is the tip. So if you take the current data from various experiments, the allowed this tip, it should be anywhere in this green region. One is 90%, another is 95%. And if you consider the oscillation data from say future experiments, then the blue region is there. But if you consider this one, this red region, this one is from all the future experimental data, then this region is coming. This means that this vortex, it can be anywhere from here to here. Similarly, this is another unitarity triangle which is very squeezed. This means that unless we will not precisely measure the tip of the triangle, it is very precisely measured in the quark sector. In the quark sector, you can see that the tip is almost to a point. So unless we will not have similar measurement in the neutrino sector, we cannot say that the PMNS matrix is unitary or non-unitary, or still there is a possibility of non-unitarity of PMNS matrix. Now, in addition, in the canonical seesaw mechanism, we require a very heavy right-handed neutrino to generate the light neutrino mass matrix, but we cannot explore the collider signature or the experimental signature of such heavy neutrino. So people propose that we can also have say TeV scale sterile neutrinos, and still we can generate the masses for the light neutrinos, and such seesaw mechanisms are known as say linear seesaw mechanism or inverse seesaw mechanism. In that case, in addition to single right-handed neutrino, you need another sterile neutrino, and you can write down the interaction term like this. And mind that there will also be other terms. So to prevent other terms, you have to use some flavor symmetries, which Srubabati is going to discuss. So once you have say mass interaction Lagrangian like this, you can write down the mass form or mass structure like this. That will give you the light neutrino mass in this form. So this is known as your inverse seesaw mechanism. So in this case, since you are having some TeV scale sterile neutrino, then there will be mixing between the light sterile active neutrino and the sterile neutrino, and the mixing matrix, it will be expanded, or it can be written like n cross n form. So this capital N, it represents the mixing of the active neutrinos, and these are the additional parameters. So we can now, because of the presence of additional sterile neutrinos, this matrix will no longer be unitary. So we can parameterize this. This matrix will no longer be unitary. So we can parameterize this matrix in this form. So this NNP, U is the usual PMNS matrix, and this NNP, it gives the non-unitarity parameters. So once you use this form for the mixing matrix, you can calculate the transition probability of nu alpha to nu beta. So Sanjay has given you one homework. I am giving you another homework. Take this value of n and find out the oscillation probability. So you will get the value of P alpha beta in terms of this n matrix, and since this n matrix is non-unitary now, this value this value is not delta alpha. When you take U alpha beta, this first term it comes as delta alpha beta, but now it will not be delta alpha beta. So using the say various experimental data, T2K, MINOS, etc. In this paper, they have obtained the bound for these non-unitarity parameters at 90% confidence level and 99% confidence level, and these are the corresponding values of 1 minus alpha II and alpha ij. So similarly, these are the allowed parameter space in different combination of these non-unitarity parameters, and you can say that you can have non-unitarity, or you can have constant on the non-unitarity parameters from the various long baseline experiments, MINOS, MINOS plus, T2K and NOVA, etc. Okay, now Dune has performed the CP violation sensitivity using the non-unitarity parameters, and you can see that if you have a large value of this non-unitarity parameter, then the CP violation sensitivity, it reduced a bit. Again, these are the allowed parameter space in theta 2, 3 and this alpha mu mu, alpha tau tau space. Okay. So now let us come to the non-standard interaction. Non-standard interaction, because the existence of small neutrino mass itself, it's a clear signature of new physics. So there are various neutrino mass models which explain this neutrino mass, and the familiar example is the seesaw mechanism and so on. So basically, when we consider the neutrino interaction in the standard model, there will be charge current interaction and there will be neutral current interaction. For charge current interaction, this is the typical diagram which will be mediated by the W version, and the vertex is proportional to usual V minus A. Similarly, for the neutral current interaction, you will have this kind of interaction where the interaction will be mediated by the neutral Z boson, and here the neutrinos, they have this vector and axial vector couplings, they are same. So they have V minus A type of interaction, whereas for other fermions like charge lepton as well as quarks, they will have different values of Cv and Ca. Okay, so non-standard interaction means the neutrinos, if they do not have this kind of vortices, then such interactions are known as non-standard interactions. So you can have both non-standard interaction in charge current transition, which are known as charge current NSI, and you can have interaction in neutral current transition, which basically affect the propagation. Coming over to charge current NSI, for example, if you have NSI in charge current, then your pi plus, it can produce a mu plus except nu mu, either nu e. It cannot produce, it can also produce a nu tau. So if you are getting another neutrino except muon type neutrino, that will be a signal of non-standard interaction, and it can affect your source. Similarly, if you have electron type neutrino and it interacts with a neutron and it produces, instead of producing an electron, it produces a muon, then this is non-standard interaction which can affect the detection process. So you can write the non-standard interaction, or you can just parameterize the non-standard interaction in terms of these small parameters, and other structure you can take same form as the standard interactions. So the picture really you can represent like this. In the standard interaction, you have, say, whatever be the this alpha, it should be same alpha, whereas if you have non-standard interaction, this alpha and beta, they will be different. So the mediating particle, the mediator of non-standard interaction will be quite heavy, so that the strength will be suppressed with respect to the standard interaction. So generally, you can analyze your non-standard interaction in this form. This is your usual, this is not standard model, standard interaction. This is the vacuum and this one is the matter effect. And if you have, say, non-standard interaction or non-standard interaction Hamiltonian, you can parameterize like this. So the diagonal parameters, they are considered to be real, whereas the off-diagonal parameters, they are considered to be imaginary. They have both phase as well as magnitude. However, since your experiments, they are not sensitive to the this non-standard interaction, they depend on the flavor. So the experiments, they do not measure, or they do not clearly measure the values of epsilon alpha beta f. Therefore, we have to sum over this f, and we can, if we take our the propagating material or earth material to be electrically neutral, then you can parameterize these combinations in terms of a single parameter epsilon alpha beta, which is the combination of all these three forms. So if you take if you take the perturbation theory and calculate the transition probability, say nu mu to nu e, then you can say at the leading order you can have the transition probability, which is the standard interaction and then non-standard interaction, and this is the form that you will get. So now let me just give you a simple example how you can generate this non-standard interaction. So it requires basically the existence of new particles. So we can consider a scalar doublet and a charge scalar doublet, charge scalar singlet, and we can have some additional Z2 symmetry. That is, under this Z2 symmetry, these new particles as well as say ER, they will be singlet, and all the standard model particles, they will be even, and these particles, they are odd. So to realize this non-standard coupling, you can couple these eta, ER, these are all Z2 odd, so they will form a Z2 even, and you can combine with the standard model lepton doublet, and this will come out to be singlet. So this is the interaction Lagrangian that you are getting. So once you take this one, then you can generate your interaction Lagrangian or dimension 6 operator. So this will give you this form, and notice that this one is S minus P and S plus P typed. So you have to use the Pierce transformation to get the usual V minus A form. So this part is coming out to be say V minus A, this part is coming out to be V plus A. So and when you compare with this one with the standard charge current mediated W boson, this one is this form, and when you take the Pierce transformation, it is coming out to be like this. So you compare this one with this one, and that will give you the value of this NSI parameters, which is coming out to be this value. So to have a small value or large value, you have to vary the mass of this m eta, that will generate you, or that will give you the value of this NSI parameters. So what is the okay? So recently we have seen that there is some tension between the value of the delta Cp measurement by T2K and NOVA. Both these experiments, they prefer normal ordering. No strong preference for Cp violation. No, but this NOVA, it measures the value of delta Cp to be 0.8 pi, whereas T2K prefers the value of maximal Cp violation, which is of the order of 3 pi by 2. So there is a slight discrepancy between these two experimental measurements at 2 sigma level. Okay, so NOVA and T2K experiments, they basically both are long baseline experiment, but they differ in their baseline. One is 810 kilometer, other one is 295 kilometer. So since there is long, this baseline is long for NOVA experiment, the matter effect will be large for NOVA and matter effect will be small for T2K. Therefore, it is expected that the effect of non-standard interaction will be more for NOVA and it will be less for T2K. So considering the effect of NSI, there are two groups. They have shown that if we take the value of epsilon E mu, the NSI parameter, to be this value and the corresponding phase will be this, then we can easily explain, or we can easily explain the tension between the NOVA and T2K. So this is the effect of non-standard interaction. Okay, so since I do not have much time, okay, so let me give you another example or another theory by which we can generate this large value of NSI, which can be used to accommodate the tension or resolve the tension between NOVA and T2K. So this is a model with leptoquark. We know that leptoquarks are hypothetical gauge boson particles which simultaneously couple to both quarks and leptons. So there are various types of leptoquarks, scalar as well as vector. So here we consider a particular value of particular form of leptoquark which transform as 3 bar under SU3, 3 under SU2L and 2/3 under U1Y. So here the charge is related to the isospin and hypercharge in this value. So there will be 3, since it's a triplet, there will be 3 charge particle. One is 5/3 charge, one is -1/3, another is 2/3. So the recipe, when you consider any new physics model, is the recipe is that first you have to write down the interaction Lagrangian, which should transform as a singlet under standard model gauge group, and after that you have to use you have to expand this one and then compare with the standard model interaction Lagrangian. From the comparison you can get the coefficient of the NSI parameters. So here after expansion, okay, after expansion the effective Lagrangian is coming out to be like this, and these two forms, they will basically have the same, they will affect the propagation of alpha type neutrino to beta type neutrino. So you can see that there is a transition of alpha type neutrino to beta type neutrino. So you can have these two kinds of leptoquarks. So you are getting this kind of interaction Lagrangian, and when you compare these interaction Lagrangian with the standard neutral current NSI Lagrangian, you can get the values of these NSI parameters which are coming out to be like this. So once you get the correlation between the quark and these NSI parameters, then we have to use the constant from the lepton flavor violating decays or any measured value, observable effect, and then constant these NSI parameters, for which one can use this lepton flavor violating decays pi 0 going to mu E, and that lepton flavor violating decays, it can be mediated by this leptoquark, which will give you the value of these leptoquark parameters like this. So basically from this lepton flavor violating decays, we get the NSI parameters which has to be less than 0.9, because this branching ratio is not precisely measured. We have only the upper limit, that is why we are getting only the upper limit of this one. So this value of say epsilon E mu, which should be less than or equal to 0.9, it is consistent with the value that is required to explain the resolve the ambiguity between nova and T2K data on delta Cp. Okay, so let me just skip this one. Now let me briefly discuss about the electromagnetic properties of neutrinos. So we know that neutrinos are special, they do not have electric charge, but still it is possible to have electromagnetic interaction for these neutrinos. So these are the ways by which you can couple a photon to the fermions. So if the fermions, they are having say electric charge, then you can directly couple to the photon to the charge fermions. However, in case of neutrinos, since they do not have electric charge, we cannot directly couple the photon to the neutrinos. You can couple them through the loop, and if the incoming and outgoing neutrinos, they are same, then this one is known as your electric, and or this will give you the electric dipole moment as well as magnetic dipole moment. Whereas if this one is different from incoming neutrino, is different from outgoing neutrino, these are known as transition moments. Another point is that this neutrino magnetic or electromagnetic properties, they can be used to distinguish between Dirac and Majorana. So basically we have this neutronless double beta decay, which is used to differentiate between Dirac and Majorana. However, if we can measure the electromagnetic properties of neutrinos, then also we can discriminate between Dirac and Majorana neutrinos. So this is how we can write the, generally we write the Lagrangian. There will be a current and there will be the gauge boson, and if we take the current between say matrix element of this current between initial and final fermion states or neutrinos, then we can write this one like this. And this form, by using the general properties of Lorentz invariance, it can be written in terms of this one, because here in addition to the free parameter or P and P prime, we can also have Q, which is the momentum transfer. So here this one is known as charge radius, this one is magnetic dipole moment form factor, this is electric dipole moment, this is anapole moment. So when the fermions, they couple to a physical photon, that is, if we calculate the values of this form factor at q square equal to 0, they will give you the electric and magnetic form factors. Now these values are different for Dirac and Majorana neutrinos. So if we calculate the loop function, then this mu I electric dipole moment and magnetic dipole moment for Dirac neutrinos, it comes out in this form, where this one is the loop factor, and for ml is the charge lepton in the loop, and mw is the w mass. So this value is very small, so we can take the approximation of this loop function, which is in this form. So in this case, you can notice that for magnetic dipole moment, this is the summation sign, whereas for electric dipole moment, this is the, you have to subtract mi minus mj. So for Dirac neutrino, this value is coming out like 10 to the power minus 19 mu b or Bohr magneton. However, for Majorana neutrinos, using the CPT theorem, this electric as well as magnetic dipole moments, they are coming out to be 0. So if you can measure the values of these electric and magnetic dipole moments, then you can differentiate between Dirac and Majorana neutrinos. Now the other one is when incoming neutrino is different from outgoing neutrino, then you can have the transition moments, and these are the expression for the transition moments. So the transition moments is suppressed with respect to, say, W mass. This value is very small, and in the previous case it is of the order of 10 to the power minus 19, whereas in this case this is 10 to the power minus 23. And since now mi is not equal to mj, you can have both electric as well as magnetic dipole moments. Similarly, for Majorana neutrinos, this is the expression. You can have non-zero values of magnetic dipole moment. This is the expression, and since in the denominator here it is 16, here it is 32, therefore the transition moment for Majorana neutrinos, it should be greater or twice the transition moment for Dirac neutrinos, but this value is very small. So these are the mathematical expressions for transition moments for Dirac and Majorana neutrinos, but how can we measure them? So these can be measured by neutrino electron elastic scattering, and John in the morning he was mentioning about the importance of this neutrino and electron scattering. So in the standard model, you can have you usually know the form of the interaction, so you can calculate the scattering cross section of say nu E cross section with respect to this Te, which is the recoil energy, and this is the expression for this nu E scattering in this standard model. And here we know all the values except this recoil energy, which can be measured in the experiment. And if there will be magnetic moment, or if the neutrinos they will have electromagnetic interaction, this will be the corresponding scattering cross section formula, and these two cross sections they can be added in coherently. So this is the total cross section. So you can notice that if we can measure the scattering cross section at very low recoil energy, then this term, since it is proportional to 1 over Te, this will give, or this will cross section will increase. So if you plot, for example, this is the red curve is the standard model or the standard model cross section, where and these curves they correspond to the cross section due to electromagnetic properties, and if the electromagnetic properties are large enough, say of the order of 10 to the power minus 11 or 10 to the power minus 10 Bohr magneton, then at low recoil energy you can see the enhancement of the scattering cross sections. So once you get an enhancement in the scattering cross section, you can find out the value of the magnetic moment, transition magnetic moment. So since my time is over, I will just give you a simple model. So if you consider as a vector-like fermion triplet in the vector-like fermion triplet and one inert scalar, which will transform under the standard model gauge group like this, and we can impose another additional Z2 symmetry, and all the new particles, they will be odd, and the standard model particles, they will be even. Then you can write down the interaction Lagrangian. As the recipe says, you have to include all the terms which will transform as a singlet under standard model gauge group. Then you can generate the neutrino mass at loop level, and you can also have the magnetic moment. So this is the expression for the magnetic moment, and this is the expression for the neutrino mass, which can be generated at one loop level through radiative seesaw mechanism. So you can simultaneously satisfy the mass generation. You can also explain the or you can also have neutrino magnetic moment in this simple model. Okay, so this is my conclusion. So neutrino experiments, they provide an ideal platform to explore a variety of new physics scenarios. Hopefully we'll get some interesting new physics signal from the upcoming long baseline experiments. Okay, thank you.
So thank you, Rukmini, for a very nice, clear and interesting talk covering various aspects of BSM searches. So questions?
Ma'am, you said that mini boon has anomaly for this sterile neutrino.
Yes.
Then initial study of microbeam shows that the anomaly has gone. Then after some analysis, they have shown like there has to be this sterile neutrino. So what exactly was that? I didn't get that.
Like as John was mentioned, like we do not have complete understanding of the neutrino nucleus cross section. So as Sajad was also mentioned, they have considered only few something. So there will be some delta resonance. So some part they missed. That is why.
Okay.
So it is related to your neutrino nucleus scattering cross section.
Okay.
Mini-boon has a low energy anomaly. So mini-boon sees some excess events at low energy, and because they cannot distinguish certain signals, and microboon was designed mainly for that,
Liquid
to see
argon.
that if they can have that low energy anomaly or not. So they don't see that anomaly, but that doesn't rule out the sterile neutrino.
Actually, mini-boon use CH2 mineral oil and microboon liquid argon tip.
That's why they have a good So microboon is part of a 3 detector setup called the short baseline neutrino detector, and these two other detectors are there, and together they can see that wave. Which
There are two other detectors, SBND and Icarus. So it will take another few years to get the result.
Thank you.
My question is, so we generally say that the mixing is between the weak eigenstates and the mass eigenstates. So if we include the sterile scenario, then since sterile is not interacting with the W or Z bosons, it is not the weak eigenstate, right? So in that case, like what are the states which are mixed with each other? So like this is not anymore weak eigenstates mixed.
No, as long as your quantum numbers are allowed, they will mix with each other. So it's not like whether they interact with Z boson or not.
But what we have to do is, when we have a sterile neutrino, you have to go to the mass basis. Then you can see through that it is interacting with the W.
Otherwise, your sterile neutrino is completely independent. If it will not mix with active neutrino, then how you can
So
see?
the kind of non-unitarity that she mentioned, it can also arise like these low-scale seesaw models. And there, when we do, these can be also searched at colliders. We have to express because you have now the mass states, right? So we have to explain the whole thing in the mass basis. There you can see the interaction.
The mass you have nu 4.
And now, if it is really almost sterile like, then nu 4 dominates in the nu s to make the nu s, or nu s dominates to make nu 4. Other component, because of the non-neutrality, because your other parameters are not precisely measured, there is a slight room that you can invoke other flavor component to make the nu s. You understand? But that will not violate the left bound, because there you are seeing those two W and C mediated processes. So as she mentioned that you can still have a mixing and keeping the bound left bound. An oscillation experiment because of the mixing.
Yes.
Because of the mixing. Correct. I agree. I agree. So this is again a weak eigenstate,
But it is not in,
in
yes, it's not under standard model interaction.
Kind of general question. So you wrote down this operator, right? The 6-dimensional operator, which also appears in flavor physics. So do you feel that the neutrino experiments will have more sensitivity to the than the Bell 2 or zeta?
No,
or
neutrino experiments basically, here you are measuring only the oscillation probabilities. They will not give you any direct
Yes.
result related. In flavor experiments, you are directly observing some decay channel and you are measuring the CP evaluation parameter or branching fraction like that. Here you can correlate.
But it will be less sensitive than the
Yes,
flavor.
yes.
And the GF that you have factored out always in the NSI interaction. So, like, is it to like if I interpret it as 1 by lambda square, then
Yes,
then
yes. This one is similar to order of mw square by m new physics square.
Yeah, but then the lambda comes out to be around 500 GeV, right? If 1 by lambda square is GeV by root 2.
Lambda value, it should be much higher than your W mass value. So
Okay.
that will be of the order of 10 to the power minus 1 to minus 2.
Yeah. Okay.
So in the standard model, the mediating particle is W. So here the mediating particle, it should be much higher than your W mass, at least more than 500 GeV. But up to 500 GeV, so far we have not seen any new particle in collider.
Yeah, so that's
it
what
should
I
be
was
greater than
confused
TeV.
with. Yeah.
Yes.
Yeah.
Yeah. Like you can have various type of leptogenesis. One is say vanilla leptogenesis, one is say TeV scale, one is resonant leptogenesis, various types of leptogenesis. Yes, so usual leptogenesis is more than say 10 to the power 12 here. You can say TeV scale leptogenesis from say resonant leptogenesis here from radiative seesaw mechanism. Here leptogenesis via oscillation. This is like not my slide, so I am not sure from what
This
is.
This is the ARS mechanism. That is also there. It's called through oscillation. So you have a thermal leptogenesis, then as she said, this TeV, and this via oscillation is the ARS leptogenesis.
Yes, yes. So here I think the oscillation is between say heavy neutrinos, so that there will be new leptonic CP phase in the oscillation of heavy neutrinos. It is not related to the yeah, delta CP of PMNS matrix.
In general, we cannot relate the delta CP of the PMNS
As to with the
leptogenesis.
yes.
In general, we cannot. cases only we can. But here there can be additional.
Yes.
Yeah, if non-unitarity comes, then there can be connection between the CP phase and the leptogenesis, because when we are calculating the lepton asymmetry, we assume U dagger U to be 1. But if your non-unitarity is large, then there can
yes,
be
yes.
some connection. That is already done. There are some papers by Warner Rodejohan earlier, long time back. We also did recently, 2 years back, some paper on this kind of non-unitary effect on leptogenesis. There was also one paper by Steve Blatchett on this kind of things. Those Sylvia? Okay. Okay. That I don't remember. But this earlier paper was by Warner, first paper.
Okay.